Number 75, salicylic acid, which is HOC6H4CO2H, and its derivatives have been used as pain relievers for a long time. Salicylic acid occurs in small amounts in the leaves, barks, and roots of some vegetation, most notably historically in the bark of the willow tree. Extracts of these plants have been used as medications for centuries. The acid was first isolated in the laboratory in 1838. Fascinating. But now let's get to the good stuff. Letter A. Both functional groups of salicylic acid ionize in water with the Ka of 1.0 times 10 to the negative third for the CO2H group and 4.2 times 10 to the negative 13th for the OH minus group. What is the pH of a saturated solution of the acid? And they tell us that the solubility is 1.8 grams per liter. Okie dokie. All right, so since we see that they give us two Ka values, we have a Ka of 1.0 times 10 to the negative third, and then we have a Ka value of 4.2 times 10 to the negative 13th. This tells me that salicylic acid is a diprotic acid. And with diprotic acids, you will always work with the higher Ka down to the lower Ka value. So at the moment, we don't even care about this 4.2 times 10 to the negative 13th because the first proton, or the hydrogen that's going to go, is always linked with the higher Ka value. So we can basically call this Ka, Ka1. So, with like any other Kas, they go with balanced equations. So let's first write out that equation for salicylic acid. Now for this one, it's HOC6H4CO2H. And remember, with acids, I don't really like to, do the whole H2O stuff, right? I just like to just say, okay, this ionizes. It's in equilibrium because salicylic acid is not one of the 6 strong acids. And they're saying that this Ka value goes with the hydrogen in the CO2H. This is called a carboxy group if we're going into organic chemistry, which hopefully on this channel we will get there. Fingers crossed. Love organic. But anyway, so this Ka is talking about this hydrogen at the end of the CO2. So on the compound, it's this hydrogen right here. This is the hydrogen that's going to dissociate and go to the base. But in this case, all we just have to say is what we have left. We have HOC6H4CO2, and that's a minus. And then we have that H plus, and that's aqueous. Okay. Now just know that also every weak acid or weak base that you have, so salicylic acid, is also going to be aqueous. Okay. So now we're dealing with Ka values. We're dealing with weak Ka values. We want to find the pH. And remember, the pH, if we write this over here, the pH, and maybe I'll write it up here. The pH, if I want to find the pH, the first thing I have to find is the H plus concentration, right? Because there is one formula. If we want to find the pH, all we have to do is take the negative log of that H plus concentration. And this is always at equilibrium. So I have to get equilibrium concentrations. That seems like a nice table to me. The E in ice stands for equilibrium. So let's just write it out. Okay. So ICE. And usually they would tell us what we're starting with here, right? But the only thing that they said was that it was a saturated solution of the acid. So in this case, we only have the acid, the salicylic acid. Acid goes with acid. So I only have initial of my salicylic acid. But remember, if we're using this ice table, it has to be in molarity. And remember, molarity is just moles divided by liters. But they gave us a solubility. But if you see, they gave us 1.8 grams per liter. And if we want to use this chart, we just have to convert the top unit into moles per liter. The liter is exactly the same, so we don't have to do anything for that. The only thing is that we just have to convert the grams into the moles. We know how to convert grams into moles. That was like way back in the day. Gen Chem 1. So let's just do it quickly. 1.8 grams of the acid, so salicylic acid, HOC6H4CO2H. Times by that ratio. Throw the unit you don't want on the bottom, HOC6H4CO2H. Mole up on top, HOC6H4CO2H. And if we're using the balanced equation, remember it's 1 mole for whatever the weight is on the periodic table. So let's just quickly find that out. I wish they told that to us in some of the questions, but beggars can't be choosers. So 1 plus 16 plus 6 times 12.01. Then we got 4 hydrogens coming in. Then we got 1 carbon plus 2 oxygens and then 1 final hydrogen. So roughly we get 138.118. Grams cancel out with grams. Let's just do that conversion. 1.8 divided by the 138. And we get 0.01303. Since this is not the answer, I don't want to give it in the correct sig figs. You should always leave yourself a little bit more sig figs than you should. But remember, this is the moles. And that's all that we changed here. So this now is the same as saying 0.01303 moles per liter. And now that's a molarity. So now that number goes here. So I have 0.01303 up top here. They didn't state that we had any conjugate base or the hydronium ion in the start, so I gotta assume that it's 0. Pause the video if you need to. I'm just going to get rid of this, stuff here because there's probably way more math that we have to do. So this is going as well. Okay, now back to the ice table. If you have nothing, remember you could only go up from there. So the product side would be plus, and the reactant side would be minus. At this point in time, we do not know how much. So let's just give the variable of x. So minus x, and plus x. It's all a 1-to-1 ratio, so it's just 1 x's. And then your equilibrium is just your initial and your change combined. So this would be 0.01303 minus x. 0 plus x is just x. 0 plus x is just x. So now, remember, we're going to take that with the first Ka value. So Ka in this case would equal something divided by something, right? It's always your two products, and they're being multiplied by each other divided by your reactant, right? So in this case, it would be HOC6H4, oh boy. Let me pull this. CO2 times H plus, and then the salicylic acid, HOC6H4, oh boy. There we go, CO2H. So now the Ka value, 1.0 times 10 to the negative third equals the two values on the top times by the one on the bottom. So we have x times x divided by, now here's the catch, guys. If we include this minus x in here, we're going to have to do the quadratic formula. And we try to avoid it at all costs. So we do like a trial run to see if we really need to include this minus x. Now, I see that this Ka value is, it's pretty small, but it's not really that small. We're not talking about 10 to the negative 11th, right? Now, what a small Ka value just means is that At equilibrium, you should have mostly reactants, and the smaller Ka value that you have, the more reactants you're going to end up with at equilibrium. But if you started with all reactants and you're ending with mostly reactants, the drop between initial and equilibrium is like just a small drop in the pond, right? We're not talking about a big decrease. We're talking about just a small little thing. And if it's just so small, this change really doesn't make a difference. So we just try to see if we could get away with it. So we're going to just say that, okay, maybe it's a really, really small change and it makes no difference. That's going to be known by the 5% rule, which we'll see in a little bit. But right now we're just going to assume that we can do that little trick. And we do the math. So this would be x squared equals, we're going to cross multiply those two numbers, 1.0 times 10 to the negative third times 0.01303. And I get 1.303 times 10 to the negative fifth. We're going to square root that x. That gets rid of the square. And since this is an answer now, right? Well, technically not really because it's not the pH, it's just the H+. But let's just say that we have 0.00361 molarity. Now let's do that 5% rule. And how you figure it out, and maybe I'll just say, does it pass the 5% rule? If this passes the 5% rule, you will take that number, 361, and divide it always by your initial, 0.01303, and you times by 100. If this number is lower than 5%, we can just keep going with the math. But if we get a number that's higher than 5%, we got to go back and we have to include that negative x in our calculation. So fingers crossed. Oh boy. 361 divided by, I think I already know the answer, but I got to see it for myself. Oh my goodness. 27%. Way higher than 5. So we got to go back. We got to go back and we have to say, I can't get rid of that minus x when I do the math. I have to keep it in there. So we're back to basically, not square one, but basically I have to include that x. So pause if you need to, but this is all going away because we're going to come back here and we're going to say, couldn't have got rid of it. I need to include that. And now when we do the cross multiplication, remember this is distribution, right? So I'm distributing this into this number, and then I'm also distributing it into x. So let's see. We're going to get x squared equals the 1 times 10 to the negative 3 times 0.01303. So 1.303 times 10 to the negative fifth minus 1.0 times 10 to the negative third x. And here is the problem because I have an x squared and I have an x. That's the quadratic formula. So what we're going to do is remember with the quadratic formula, you get everything over to one side. So I can just plus 1.0 times 10 to the negative third on both sides. And maybe if I just show that over here, I'll bring this over here a little bit. So I can say on this side of the equal sign, it's plus 1.0 times 10 to the negative third x. And then this number is positive, so I have to subtract it. And I have to minus 1.303 times 10 to the negative fifth. Okay. So because of that, this cancels, and this cancels. That whole side equals 0. And now if we just clean it up, it would be x squared plus this minus this. And I just need a little bit more room. There we go. Pause the video if you need to. Just going to get rid of this. And I'm going to try to scooch this over. So this I don't need anymore. I'm going to try to bring this over. Beautiful. Right into that little pocket. This is what we're going to be working on. Now remember, with the quadratic, we need a, b, and c. A is the number right before the x squared. There was no number, so it's a 1. B is the number right in front of the x. Got to take into consideration the sign. This one's positive, so that's okay. So 1.0 times 10 to the negative third. And then c is just the random number at the end. It's a negative, so I have to include that negative. Negative 1.303 times 10 to the negative fifth. Now we plug all these numbers into the quadratic equation, which is this one right here. We love it, right? We love it. So let's see. I'm just going to move stuff around here. I'm going to get rid of, I think I can get rid of this. Let me see here. I'm going to get rid of this. And maybe I'm just going to pull, because this is not in a good spot. I want to pull this over here. There we go. Just to give myself a little bit more room. And maybe I'll put these at the bottom here to reference. But basically, I'm just going to plug in everything that I got for the B's, the A's, and the C's. So we're still trying to solve for x, right? So x equals something divided by something, negative b. So the b was the 1.0 times 10 to the negative third, plus or minus the square root of b squared. So 1.0 times 10 to the negative third, that's squared, minus 4 times the a, which is 1. So basically we don't even have to do that. And then times by c, which is, if I just grab this over here, I think now I have a little bit more room, negative 1.303 times 10 to the negative fifth. Okay. And now this is all divided by 2. Maybe let me close that up. 2 times 1. So I'm just going to work off of this one. Right, so 2 times 1, we could just simplify this by saying this is just 2, right? So whatever I do on the top, I'm just going to divide everything by 2. And now what we're going to do is we're going to plug this whole thing under the radical into the calculator to get one number. So I'm going to just go into the calculator. I'm going to say, okay, I have 1 times 10 to the negative 3, and that's squared. Then I'm going to get 4 times 1, so that's 4, right? So 4 times a negative 1.303 times 10 to the negative fifth. And then I'm going to do the answer to that minus this. And okay, so I'm just going to erase everything under here because I got this as one number. And that is 5.312 times 10 to the negative fifth. Let's now just take the square root of that. And I try not to round, but this one has a lot of numbers, so maybe I'll just round it a little bit. So this will be 0.00728835. Okay, now we have two options. I can either do this number plus this value, or I can do this number minus this value. That's what the plus or minus means. Remember, you can only have positive molarities, especially since we're just solving for x. So one of these is going to give us the positive answer, and the other one's going to be a negative, right? But if I'm starting off with a negative and I'm minusing a number, I'm becoming more negative. So the minus route will get me a negative value. So I know that that's not the correct one. So I'm going to use the plus value here. Now you could do both and just see on your own that, there are two options, but you always pick the positive answer. So let's do negative 1 times 10 to the negative 3 plus 0.00728835. Okay, so now I'm going to just erase this because now I have that as one number. And I have 0.00628835. 0.335. And now we're just going to take that and divide it by 2, and that's our x value. So x equals, we'll say 0.00314. Okay. So maybe I'll just, make this a little bit nicer. And that's what the H plus was. H plus was X. So I know that the H plus concentration is 0.00314. Now technically, since this is a diprotic acid, we should flow through the whole thing again with 4.2 times 10 to the negative 13th. But this number is so small. The smallest that you can get is 10 to the negative 14th. It's right there. This basically means that you're not going to have any additional ionization of H plus in the second equation. If you wanted to do that though, go for it, but you'll see that this number won't budge. So we're just going to take this answer and find the pH. So pH equals the negative log of that number, which is 0.00314. And we're finally going to get an answer for letter A. So negative log of 0.00314. We'll say 2.50. And that is your final answer. So it's pretty acidic. 2.5 is pretty acidic. All right. So this was letter A. Hang tight for letter B in a little bit. If you guys are on the playlist, I highly recommend you are. Then we'll just jump right into B, and then you have both answers figured out. Hopefully it's not another quadratic, but you never know. So we'll see. Thank you so much. Please subscribe to the channel if you want to help us out, and I will see you all in later lessons. Okay, bye-bye.